Hi there, welcome back. If you're a follower of my channel, you may remember that some time back I built a balanced line driver. This was it. The reason I built this is that I was repairing an amplifier that had balanced XLR balanced inputs, and although I could have tested it with normal BNC to balanced converter, I wanted to actually test the full function of the balanced inputs. And at the time, as I had no balanced line source, I had built this balanced line driver. And what it basically does is it takes an RCA input, a normal single-ended audio input, whether it be from a signal generator or from an audio source, and it converts it to a balanced signal. Now, if you don't know, a balanced signal takes this signal going in here. It produces that on one of the pins. It produces the exact opposite, in other words, the negative version of that, the inverted version of that on one of the other pins, and the third pin is ground. Now what this does is it allows you to transmit or to carry signals over long distances with less common mode noise. That means that as your cable, the longer your cable is, the more noise it's going to pick up. But if you have two signals and they're opposite to each other, they both pick up the same noise along the way. So when you feed them into a balanced input, the two common modes cancel each other out. And therefore you can actually run these signals over long distances and reduce the noise pickup. Now, when I built this, I explained that I took the schematic from the web. It's all over the place, no big deal. It just uses an op amp per channel. It's a dual op amp. And basically what it does is it takes the single-ended signal, it feeds it into the circuit. There's a 10K resistor to ground, which acts as the input impedance. Then it feeds it into a unity gain buffer, and that signal is basically passed straight through and comes out at the hot pin of the XLR output, or the balanced output. It simultaneously takes that output, which has been buffered, and flips it. In other words, passes it through another unity gain buffer with an inversion function, which is just another part of that op amp. It's an inverting unity gain amplifier, and it feeds that to the cold pin, in other words, to the inverted pin. And so you get the signal and the inverted version of that signal coming out of the XLR, which is basically what a balanced signal is. This one has a 100 ohm resistor at the output, which just helps with any, or prevents any oscillation if it's going into long cables with capacitive function or capacitive characteristics. It avoids oscillation. It also sort of acts as a guard against absolute short circuit. If it does short circuit, then at least you got, or the op amp has a 100 ohm load. Looking at the power supply, what this uses is the typical op amp requirement, plus and minus supply. I've used 9-volt batteries in the past, actually two 9-volt batteries, one there and one there, and they are wired together to give you a plus 9 volts and minus 9 volts and ground. You can use any supply that you have. I'm going to show you what I'm going to use in mine. Now, why did I want to build this again? Well, since I have been sponsored by PCBWay, I decided to do this right. And I designed a circuit board that I ordered from them. And the result, I hope, will be a neater version of this, much neater, and also a lot more stable. There's always a chance with something like this that something will go wrong. One of the solder joints, one of the wires might short. And believe me, if you have a power amplifier that's taking this signal and amplifying it to say 250 watts, which I think that amp was, you don't want any clicks or shorts happening at the time that you've got this thing connected, because if you do, you're going to blow up some speakers or your amp. So basically, I want to create a more stable version. So I went ahead, designed the board, and ordered it from PCBWay, and I received it. Again, if you've been following my channel, you know that I like to build these modules that I stick here under the workbench. They're all built on similar aluminium element which is cut off at the top, so they serve as my project boxes. This is the first one I built. It's a dummy load switcher, and it allows me to take an input signal from the speaker outs of an amplifier, and I can switch it between speaker, which is my lab speakers, and a dummy load or off. On dummy load I can run it at 4 ohms or 8 ohms, and I can also then monitor the outputs from here into the scope, which is just above there. I also built this one, which is an antenna switcher, which takes my mini whip signal and long wire signal and switches that to the output there, so I can test radios with it. The power supply is actually built in, it's very low power. And recently I built this one, which is the other project I did with a sponsored PCB from PCBWay, and that is the switchable attenuator. This one can do 3 dB, 6 dB, 12 dB and 24 dB, or any sum of those. It also has a dummy antenna that I can switch in or out when testing radios. And the next candidate for one of those modules is going to be this balanced line driver. So I'm going to go ahead and build this thing, and we'll see the result. Hopefully it'll help add to the collection that's going on here. Sooner or later these will all be stuck together, and I've got a few more ideas as to things I want to put on here. These are things that I find useful every day, and instead of having them lying around as modules, I prefer to have them accessible right on the workbench. Okay, let me get the components out and get started. So here we are. We've got the board. I've got these two capacitors. I've actually used 1000 microfarads on there. This is for local supply filtering. Now this thing will be supplied by a very good supply, whether it be batteries or a plus minus 12, plus minus 15 volts. Doesn't really matter. I've marked plus minus 12 on here, but as I said, that's just what the whatever voltages the op amps require. The supply is going into one of these, which makes it easier to connect. I'm putting the ICs on IC sockets, so that if I don't like the particular op amps that I've got on there, I can swap them out. The two local decoupling on the power supply caps, these are ceramics, and then I've used these 0.6 watt resistors. Now the key to getting a very good balanced signal, in other words, the key to getting a signal which is, you know, very accurate in terms of inverting the basic signal, depends on your resistor values. The gain of that second op amp is based on the accuracy of the 10K resistors. So if one is 10K, one's 11K, you're not going to get an exact times 1 or minus 1 gain. And that means that your top signal and your bottom signal, or your hot and your cold, are not going to be exact replicas or opposite replicas of each other, mirrors of each other. So these are, well, I think 1% resistors. You can use 0.1% resistors, but as long as they are fairly accurate, and I've measured these guys, made sure that they're pretty accurate, just within one resistor lot. And now it's just a question of getting it all there and soldering it and seeing how this board behaves, because this thing should solder quite well. I've made the pads big enough. I've done this in through hole for the simple reason that some of the projects I've done on these sponsored PCBs have been surface mount. Some people still have a problem with surface mount. I must admit, I used to be one of them till I tried it, and then I don't want anything else. It makes it so much easier, but I do understand that you may not be too keen to stock up with components just for surface mount. I have quite a mixture of those, so it's not a problem for me. But I've done this one through hole, makes it easier for anybody else who wants to do it. So let's get started. What I've done here is I've put in the resistors first, and I've actually checked values, looking at the schematic, making sure that I've got the resistances that I need. It's quite easy when you don't have any other components in here. Just make sure you've got the right resistors in the right places just before you start soldering. That's just what I like to do. All the resistors are in. The soldering is very, very easy on these boards. I really have to compliment them on the quality. You get, because you've got the through hole, and it's, when you put the solder down here, you can see that it flows through and actually does the soldering at the top end as well. It really, really looks professional. So I'm very happy with that. Next. Small components first. Here we go. These caps. These are just bypass on the supply. I'm using these ceramics. Probably should have done a smaller footprint, but that'll do. So these ceramic caps can go in next, and also the IC sockets. Make sure I got that right. There's one there. And the other one is there. So I'm ready to solder those. The sockets I'm going to have to hold down while I just solder the one pin so that it holds in place. Let's see how we get along. What I normally do is I just get the solder up here, touch it to one of the pins. There we go, got the one pin. Make sure that it's flat, nice and flat, and we're ready to do the others. I'll do the same with this one here. Just get that one pin. Here we go. I believe that's done. What I can actually do now is I can actually put these caps in as well. Just bend them a little bit on the underside so they hold onto the board. Make sure that they are nice and flat. Actually, I prefer to do the same thing with this one. I hit the one pin with solder, push it really flat, make sure that it's in place. Yep. And then I'll do the other pin and redo the first one if I need to. There we go. I think that's it. Now I'm ready to solder the rest. Get the helping hands again. And we're ready to go. And there we have it. So, what do I need to put in here? The sockets. Let's do that. On these bigger ones, on these bigger connections, I do use flux. I don't normally use it on the single component stuff. Doesn't need it. So, we've got our board done. We'll just need to put the op amps in there. We need to provide the supply. And then I need to connect the plugs and sockets to this. Now what I'm going to use, this is what this thing was designed for. It was designed for these sockets. XLR, they're male, and the logic is that whenever you do something with an XLR, the pins always point in the direction of the signal. In other words, this is an output, therefore the signal comes out of here, therefore it comes out of pins, therefore it's a male. that is the logic, that is the convention that's used. The RCAs have no polarity, they're just RCAs. So these are the sockets that should be used here. Unfortunately, I haven't got two of these. They're on their way, and shipping is taking ages these days. So what I'm going to do is I'm going to use the other XLRs that I've got, and then I can always change this when they arrive, but I want to get this thing done. I want to test it. I need to use it for something right now or soon. So I'm going to build it with the other XLRs, the ones that I used on. In fact, I'll probably just use these and also the BNCs. So I'll get that done. I'm going to put it into this box for now until I receive the other the XLR plugs and sockets. So I'm going to put it in this box for now, and then I'll be able to test it, see how we got along. And here we are. The board has been completely soldered. All the components are in. The two op amps have been put in there. Make sure you get them the right way around. Don't ask me how I know what the consequences are. It's happened. For test purposes, I put it in here. I've connected the XLRs. There's the one to the left, or the right channel. The left channel. There's the left in, right in. These are two isolated BNCs. Everything's isolated from the chassis, and that is on purpose. Everything is in fact isolated from the chassis here. I'm not using the chassis as a ground, and the reason is I want these things to be completely floating with regard to the chassis, because this chassis will ultimately be clamped onto a rail that I have under the shelf there, so all of them will be sort of basically wired together, and I don't want that. So what I'm going to do now is I'm going to use two 9-volt batteries to start. What I ultimately will do is I'm going to build a, well, actually built this one on boards that I did before, and this is a plus minus supply, and I can adjust it to minus 12, plus 12, or minus 15, plus 15. Put a transformer on there, a 12012 or 15015 transformer. I want to fit this under the bench as well, so I have a fixed supply up there, dual supply. That dual supply will then feed the module, which, as I said, will be in this case. So I don't have to have separate supplies for every module I want to put up there. Most of them, if they do use op amps, they will be in the 15 volts plus minus 15 volt range. If it's something that's a different voltage, I can always use a local voltage regulator to drop the voltage. But the highest voltage I'll probably need on there is plus minus 15 or plus minus 18. Doesn't really matter. So I'm ready to test this. And what I'm going to do is I'm going to feed a signal in here in one of the channels for start. And then I'm going to put the one channel of the scope on the hot output. The other channel of the scope will go to the cold output. And the ground, I'll just use the one channel ground, will go to the ground on there. And the ground from the BNC is actually the same ground that I have there. So I have to be careful. If I do need a totally separate floating inputs, which is not normal, I can't use the two simultaneously because the grounds are common. Let's get this thing set up and let's see what the result is. And here we have it. I've got two 9-volt batteries on there. They're powering the plus 9 minus 9 instead of plus 12 minus 12. I have the hot output going to one channel, cold output going to the other channel, common ground. The BNC is coming in here. It's coming from the signal generator, 1 kilohertz signal. And let's see what the scope tells us. And there we go. What we're seeing here is the hot and the cold, which are exact opposites of each other. They are 1 kilohertz signals. This purple line that you're seeing here is actually A plus B. And if the two are exactly the same, then A plus B must be 0. And it's giving us pretty much that. A slight amount of noise, but this thing is totally unshielded. But that's what we're getting. So what we've got here is the same gain on both channels. And if I take the math function and I do A minus B, which is exactly what happens when the signal goes into the system, then what happens? You see it looks the same, but it's not. It's actually double the amplitude. The scale is different. I've got that scale. If I take that scale and make it 100 millivolts per division, and I take that scale, make it 100 millivolts per division, A minus B, which is what happens when this thing goes in, actually gives us double the amplitude. And that's exactly what we expect from a balanced line signal. So our balanced converter, or single-ended to balanced converter, is working perfectly well. The other thing is, I can hit it. I'm hitting it, and I don't get any glitches. And as I said, the problem with feeding a signal like this into a power amplifier at full preamp amplitude, I mean, at the moment I've got 100 millivolts, but I could up that as long as I take care of, let me get rid of the math function. As long as I take care of these guys, I can up that 200, 300, 400. They're on different levels. Idiot. There we go. 1 volt per division. 6, 7, 8, 9. There's 1 volt per division. Rather 1 volt RMS coming in. I can up that, and they both adjust accordingly. So if I've got that sort of signal, 1 volt, 2 volt RMS going into a power amp, coming out of this thing, going into a power amp, and there is a glitch because I touch the component, or one of these solder joints is not well done, anything like that, the spike that'll go into the power amp is going to get rid of it. It's going to damage it, which is the reason why I wanted to do this on a more viable and a more secure board. And that is exactly what we've got here. So again, I want to thank PCBWay for sponsoring this video and these boards. If you're interested in these boards, I'm going to put the Gerber files on the description below. You can just order it from them. It's very simple. You just go to the website and you place your order by putting in the size. You put in the size of the board and you select the characteristics of the board. This thing is $5, 10 PCBs. It's incredible. It's very, very cheap, and it's cheap enough to make someone like me look professional. You can just use those Gerbers, by all means, make use of them, order your boards, and go ahead and build it if you need it. Once again, thank you very much, and once again, PCBWay, happy birthday, happy anniversary. Hope you're around for many, many more years, because people like me need you. Thanks for watching. Bye for now. Stay safe.